Okay, we drew a figure a couple lessons ago that I said will come into play quite a bit, and that is what looks like this, not that, this. And I can do better. That's better. Okay. A normal curve, or as you've commonly said, a bell curve, bell-shaped curve. That is a, whoops, where'd it go? A bell or bell-shaped curve. And we know that right in the middle, said this, is the mean, because that's the balance point, the center of gravity. It's the median, because it's in the middle, and it's the mode, because it's under the highest point. It's the one that shows up most frequently. The one we care most about is the mean. So I'm just going to leave mean there because I want to give myself room to work on something. Now, we also know what standard deviation is, right? Or you've heard of such a concept as standard deviation. Standard deviation is a number that tells you something about the dispersion, or in kind of plain English, the phrase coined by the brilliant Dr. Good. The spread, it's a measure of the spread outedness. A higher standard deviation means things are more spread out. A lower standard deviation means they're not spread out as much, they're closer together. So we can think of standard deviation, since it is a distance away from the mean, sort of an average deviation score, an average of the sums and the squares and all that stuff. An average distance from the mean, taking all the different x's into consideration also. So when I have my bell curve, what I have is, let's say, along the bottom from left to right, let's say that's going to be a score of some sort. And it can be an SAT score or an ACT score, anything that's normally distributed. And most standardized tests are normally distributed. Most classroom tests, as we've decided or demonstrated, are not. But most standardized scores are pretty close to normally distributed. Some scores are above, some scores are below. If I think of standard deviation as a distance, I can look at a place on my scale from left to right that may be one standard deviation above the mean. Likewise, I can look at my scale from left to right and find a place that may be one standard deviation below the mean. Now, again, my left to right scale is the score. My vertical axis represents the frequency of something, so that's why the mean, median, and mode is under the high point. So that tells me how many times something happens. So I've got between -1, one standard deviation below the mean, and one standard deviation above the mean. Now, everything from here to here, all those scores between those lines I just drew are within one standard deviation of the mean. And it turns out we actually know a good bit about that, or a couple of important things about that. It turns out that in a normal distribution, and these probability studies and all this stuff have come up with this, that approximately, and it's real close to it, approximately 68% of the cases are within one standard deviation of the mean. Somewhere between -1 and +1. 68%. Hey, what percent of the cases are between the mean and one standard deviation above? 34, because the distribution, the curve is symmetrical, means the left half is a mirror image of the right half. So I know that 68% between -1 and +1. I know that's broken down to two 34% between -1 and the mean and the mean and +1. But 68% of the mean, that's a little more than 2/3. If I go out another standard deviation, which is going to give me plus and -2, and notice that the distance, and I've gotten pretty close here, the distance between the mean and +1 should be the same as the distance between +1 and +2. All these distances should be the same. I got that maybe a little far out to the left. I'll fix that. Close enough. Okay. So, and a little furthermore, we know that I've already used up more than 2/3, so I don't have much more to go. So between -2 and +2 would be that 68% plus some more, plus the stuff in this area. I think you can see my cursor wiggling, and this area. Turns out that we know that, and I'm going to have to give myself a little more room to write here, so I'm going to eliminate this word score. Between -2 and +2 is approximately, actually a little more than 95%. So I've already used up everything but 5, actually a little less than 5%. Now this 95%, just sneak preview coming, spoiler alert, this 95% is going to be pretty important later down the road. And I'll tell you why when it's time to. But 95% comes, or 95% of the cases are within 2 standard deviations of the mean. All right, here's a follow-up question. What percent of the cases are more than 2% of the mean above the mean? I'm sorry, what percent of the cases are more than 2 standard deviations above the mean? Above. Good catch. 2.5%, because of that 5% left over. Yeah, that's right. Of that 5% left over, again, because the symmetry, you're going to have half of that 5% up here on the upper tail, and we do refer that as a tail, and the other 2.5% of that 5% on the lower tail. So I've only got 5% left, and that's split up into 2 parts. If I go out one more standard deviation, so plus and -3, that's going to take in, give myself room to work here. Oh, that's good. More than 99% of the cases. We'll call it 99 for now, and we'll get a little more accurate as we move along. Now, do I really need to draw anything beyond plus or -3? I really don't, because I've got less than 1% and even less than half of less than 1% on either individual tail. So I don't really need to go out more than plus or -3 standard deviations. There's just not that much out there. It's just very, very, I'll use a word on purpose, sneak preview spoiler alert again, it's very rare to get beyond that. Remember the word rare. Remember the 95%, and you'll come back to it later. Remember the word rare. Those will be important. Okay. Turns out a lot of things are normally distributed, or approximately normally distributed. I mentioned standardized tests. I specifically mentioned ACT and SAT, and we'll be using some examples of those in a little bit here. If you go out and collect in the general population data, like say height or weight, height and weight tend to be normally distributed. There's a mean height that's kind of in the middle. Most people are within a or more people within a fairly short range of height than others. You got a few people who are very tall, a few people who are very short. I fall somewhat below the mean on that scale, but within that 3 standard deviations, certainly. So things are normally distributed a lot. Not everything. For example, we've mentioned things that are not normally distributed. Housing prices are not normally distributed. Salaries are not normally distributed. Classroom test grades are not normally distributed. So this works when things are, and a lot of things are. Now, another sneak preview of coming attractions is that even though something may not be normally distributed to begin with, sometimes there are some things that we can do to use what we know about this normal curve anyway. So right now, what I want you to know is I want you to know the plus and minus 1, 2, and 3 standard deviations, and I want you to know the 68% within 1, 95% within 2 standard deviations, and 1%, or actually a little less than 1%, I'm sorry, 99%, or a little more than 99% are within 3 standard deviations of the mean. Questions, thoughts, comments? Smart aleck remarks. Everybody still equally unhappy? Anything from home? Here or home? Okay.